I'm going to begin with a review of the extended law of sines. This is pretty easy to prove. We'll take a triangle ABC and put it inside of its circumcircle. Then we'll draw this segment BD so that it's perpendicular to BC. So we have a right angle here. And then I'm going to draw segment CD. And because this inscribed angle is 90 degrees, that means CD is a diameter of the circle. Also, if you look at the arc BC, the inscribed angles that cut off this arc are this angle here at D and this angle at A, so they're congruent. So in triangle ABC, the sine of this angle A is going to be the same as the sine of angle BDC. That's opposite over hypotenuse, so BC over CD. If we label this opposite side lowercase a, and CD is the diameter of our circle, let's say that the radius is r, so this is 2r. Writing this in terms of 2r, this is a over the sine of a, and without loss of generality, b over sine b and c over sine c. Let's return to the problem. I'm going to number these equations, and we'll start with the first one. I'll replace the square of the cosine of a with 1 minus sine squared a, and cosine squared b is 1 minus the sine squared. I'll subtract these two and multiply the whole thing by -1, and subtracting 2 and multiplying by -1, we get 1 over 8. By the extended law of sines, a over sine a is 2 times the circumradius. Solving for sine a, we get a over 2r, and we can square both sides. And similarly, we have sine of b is equal to b over 2r, and we can square. Now we'll substitute for the sine squared of a and sine squared b over here. I'll keep the 2, sine of a and sine of b. When we multiply these two fractions, we'll have a times b, and then 2r times 2r. That's 4r squared, and then we're left with cosine of c. We'll factor 1 over 4r squared out of all these terms, and you should recognize this as the law of cosines. This is equal to c squared. On the left-hand side, we note that by the extended law of sines, sine of c is c over 2r, and when we square both sides, we get the expression that we have on the left, so I'll replace this with the square of the sine of c. This gives us the square of the cosine is 1 minus this, or 7/8. Let's do the same thing to equation 2 in the problem statement. Again, we'll replace these cosines with 1 minus sine squared of b and c, subtract 2 and multiply through by -1. Substitute from the extended law of sines. We can see our terms here from the law of cosines. So I'll write this as 1 over 4r squared times a squared, and this is equal to 4/9. On the left again, we have the square of the sine of a, and the square of the cosine is 1 minus that, or 5/9. Let's see what we can do with the third equation. We'll proceed as before. I'll pull out the 2 and do our law of sines substitution. So this is 2 minus b squared over 4r squared, which is the sine squared of b. We don't have information right now about angle b in our triangle, but one thing to note is that our angle sum for this triangle is 180 degrees. So a plus c and angle b are supplementary, so they have the same sign. So I'll replace this sine of b with this angle sum. I'll write out our angle sum formula. That's sine A cosine C plus cosine A sine C. And now we can substitute from our earlier calculations. Sine squared is 4/9, so sine of A is 2/3. The cosine of C from here is root 7 over 2 root 2. Cosine of A is root 5 over 3, and sine of C is 1 over 2 root 2. Adding these in our numerator, we have 2 root 7 and root 5, and the denominator is 6 root 2. Now we'll square it by foiling out the numerator. We have a 28, 4 root 35, and 5. And in the denominator, this is 72. Now we'll substitute back up here. And so we're left with 111 minus 4 root 35 over 72. When written in this format, the problem asks for the sum of all these terms, which is 222. If you'd like me to solve any math contest problems, please leave them in the comments.